This is lecture 9G for Calculus 2 on draining fluids from conical tanks. When we drain the cylindrical tank, the volume included the radius of the tank, right, squared, pi, radius of the tank squared times the height of the fluid. The radius of the tank was part of the tank and it never changed. When you get to the conical tank, you have to use this other trick, and here's the idea. So now I will attempt to draw a cone. Okay, that's a cone of sorts. Right. This cone has some overall height of h. This is a physical cone. And it has some overall radius of r, the largest part. Now when the fluid, I'm going to get a different color, when the fluid is in the tank, say it's at this level, then the radius of the fluid at this level we'll call little r, and here's the height of the fluid level h. You see h and r related. If I drain more out of the tank, I'll be down here, and now r is smaller. So for the cylindrical tank, the radius of the tank was fixed. For a conical tank, the volume of the fluid depends on r, where r is a function of h. Depends on where you are. If you're completely full, then r would be equal to big R. If you're completely empty, then r is 0. So you see you have two variables here. One is r and one is h. Both of them are changing in time. You really want to only look at h, and the reason you can do that is because of this relationship right here. Now, we've used this before. That's a good thing to kind of get a handle on. Right. The ratio of radius to height is equal to the overall radius divided by the overall height. So you have this kind of proportion. With this proportion, you can rewrite that radius in terms of height. So the radius here, this green one, or this red one down here, is equal to the physical dimensions of the tank, the radius of the tank, and the height of the tank itself. That's what these two numbers are, capital R and capital H, times the height of the fluid. Now we'll take this and we'll substitute back into this equation right there, and we'll do that on the next slide. So here's the volume in the tank. Okay. It was 1/3 pi r squared h, where r is the radius at the fluid level, h is the actual fluid level. I rewrite r, remember r was equal to big R over little r, capital R over capital H, which is dimensions of the physical dimensions of the tank times the fluid level h. So I substitute that, and I end up with an h cubed. Now when I take the derivative, nothing changes but that h cubed, and I get the derivative in the conical tank. The change in volume with respect to time equals pi times the square of big R over big H times h squared dH by dt. Now we set this equal to the expression from Torricelli's law, and we develop our differential equation from that. So from Torricelli's law, again, we're going to have a circular outlet pipe. That's what we used. If you have something else, this term will be different, but we don't. Okay. The flow is negative because it's draining out of the tank. 60 pi r squared, square root of 2g, that was from before, times the square root of h equals pi times the ratio of the physical dimensions of the pipe squared, h squared dH by dt. It's not that different from the other one, except we got to do some rearranging, and we'll do that on the next page. Here I've rearranged the differential equation so that we can group all the constants together. Let's see. Here are all those constants. These don't change with time, and they really have nothing to do with our problem. And we have dH by dt, the first derivative, equals negative of all these constants, and I'm going to rename them gamma. Here's what gamma is, so I don't have to carry all those numbers around. Right. Then I have square root of h over h squared, which becomes h raised to the minus 3/2 power. This is a separable equation, and I'm going to solve it as a separable equation. Okay, so here's our equation here, written out with, okay, again, for a separable equation, you would write some function only of y times dy by dt, and the other side you only have a function of t. Okay, our function of t is gamma, which is a constant, or rather minus gamma. This term is h to the 3/2. Just rearrange the equation. Now I can integrate easily. I'm going to integrate this side, integrate this side. Remember, both of them will give constants of integration, but it's customary to lump all the constants over on the right-hand side with 1c. You don't need two constants in this case. You can put them together. You can do that because you're combining similar terms. This is not true in general. For example, if you have something where you have, let's say this equals some function, I don't know of time, let's say t cubed plus c1t plus c2. You've seen equations like that for displacement when you started with the acceleration and took two derivatives. Now this c1 is multiplied by t. This c2 is by itself. You cannot combine them. But when I integrate this equation, I end up with 5/2 h to the 5/2 plus some constant, we'll call it c1, equals minus gamma t plus c2. Now I can combine these, right, because they're similar terms, and then lump them all together with 1c. So although it seems like we're being a little cavalier about this, we're actually being correct. Get rid of all the writing now. Okay. So here's my equation. I've got the c in it. Remember, this is the general equation. I want to develop the particular equation because I'm going to specify this initial condition. The initial height of the fluid is h at 0 equals some h naught. Substitute that in, and I get an expression for that constant of integration. C equals 2/5 h naught raised to the 5/2 power. And I'll substitute that back into the equation, solve for h, and that will be my solution for the conical tank. So after some juggling around, this is my solution for a conical tank. I need to have gamma. Gamma is specified by all these numbers, and here's what it is. H is the height of the fluid in the tank. R is the radius, the physical radius of a tank of H. These are the physical dimensions, and H is one value of the height of the tank. Well, it corresponds to that radius. This is physical dimensions of the tank. All right. R is the radius of the circular outlet pipe. G is acceleration due to gravity. All right. To find the time it takes to empty the tank, set h equal to 0 and solve for t. T got kind of little there. So we can solve for t. T has to be 5 h naught raised to the 5/2 power divided by 2 gamma, and that's how long it will take to empty your conical tank. Okay, that's it for draining equations. I think we've derived Torricelli's law in a way that will allow you to use it in many different circumstances. And I can see how the little pieces came together. People tend to grab it and run with it and just quote it at the final result, but the final result really does depend on, the size, the shape of the outlet pipe or hole that's draining the tank, and that has to be included in there in that area. Okay, and sometimes when you drain tanks, people want to know how many liters, gallons, etc. So I put this little chart in here and in the written lecture notes.